Okay, in this section, we're going to be looking at congruent right triangles again, which is from Unit 2. We just went over that back in section 2.5, and it's from Math 1. But what we're going to look at this time is a couple of shortcuts for congruent right triangles, specifically right triangles, instead of just all congruent triangles. So let's see what you think about these. So congruent right triangles. These triangles have the exact same size and shape. We know this from the definition of congruence, and that their three pairs of corresponding sides are congruent. Their three pairs of corresponding angles are also congruent. This applies to both regular triangles and right triangles when we're talking about their congruence. Okay, let's go down and look at an image here. Complete the congruent statements for the two right triangles below. So notice that we're starting with AB is congruent to DE. AB is congruent to DE. And so if you look at those corners, can you see this 90-degree angle and this 23 angle that those are leading into? So one set of congruent sides was put into the study guide already. You're doing the others. Excuse me. So let's go get the other sides. How about this guy over here? The hypotenuse. So could we say that BC is congruent to EF? And could we also say that AC is equal to DF? So that's it for the sides. Now they already did A and D for the angles, A and D. So let's go do B and E and C and F. So again, those are the congruent sides and those are the congruent angles. Let's go look at what are these shortcuts for right triangles. Okay, so there's the hypotenuse leg theorem. So remember, we've already got in normal congruence postulates, we've got side, angle, side, 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 angle, side, angle, 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 side. So those are for all triangles, what we need to prove that they are congruent. But there are shortcuts for right triangles. If it has a 90-degree angle, if it is a right triangle, then there are shortcuts. We don't need as much information. So for example, this HL theorem, hypotenuse leg, is if the hypotenuse and leg of a triangle are congruent, of the right triangle are congruent to the hypotenuse and corresponding leg of another triangle, then the two triangles are congruent. So we only need two things, one hypotenuse and one leg, in order to prove congruence in a right triangle. So this is a shortcut. Let's go look at the next one. Next one says leg-leg theorem. So this one says that if the legs of a right triangle are congruent to the legs of another right triangle, then the two triangles are congruent. So again, two legs is enough. The HA theorem. Let's go purple on this one. This stands for hypotenuse and one angle. So if the hypotenuse, and an acute angle, so specifically it has to be an angle that's less than 90, are congruent to the hypotenuse and a corresponding acute angle of another triangle, then the two triangles are congruent. Again, one hypotenuse and one acute angle are enough. We need less for these shortcut ones. Finally, let's go blue. The last one is the leg angle theorem. If the leg and an acute angle of a right triangle are congruent to the corresponding leg and acute angle of another, then the two triangles are congruent. So again, just leg and an angle, an acute angle, are enough. These shortcuts only need two things to prove congruency instead of the three things that we needed before. Kind of cool, all because it's a right triangle. Okay, let's look at these next fill in the blanks here and see if this makes sense. All right triangles have a pair of congruent angles. They're right angles. Can you imagine that? All right triangles have a pair of congruent angles. They're right angles automatically. Okay. If you know the lengths of two sides of the triangle, you can use the Pythagorean theorem. Oh, hey, that's why we did that in the first section. The Pythagorean theorem to find the third side. So if two pairs of the sides are congruent, then the third pair is too. That's the key point here. Let me go ahead and highlight that. So if the two pairs of sides are congruent, then the third pair automatically is too. So the HL theorem is a special case of the side, side, side postulate. Because if you have a hypotenuse and a leg, and you use Pythagorean to find the third side, that gives us our third side, 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 side of that. The leg theorem is a shortened version, a special case of side, 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 and side angle side postulate. Because again, with two legs, you have the third. Finally, the HA or hypotenuse angle theorem is a special case of AAS, and the leg angle theorem is a special case of AAS and ASA. So all these are shortened versions of the other postulates that we're already familiar with. We just need less because these are right triangles. Okay, let's go see if we can visualize these new ones in their picture. So looking at this first one, do you see how I was given a leg, meaning the side that is not a hypotenuse, and one angle? So we would call this one congruent by the LA theorem, known as leg angle theorem. Okay, let's look at the next one. What did they give me? Notice that I've got a leg. Sorry. There it is again. And notice that I've got a hypotenuse. So in this one, I could say that it's congruent by the hypotenuse leg theorem. All right, how about this guy? Do you see how this side has a 7.2 and this side has a 7.2 and this has a 12.3 and this has a 12.3? So we have two pairs of corresponding legs. So we can say that this one would be congruent by the LL theorem, or two legs. And finally, look at this last one, how we have the hypotenuse and one angle. So this one would be able to be said congruent by the HA theorem. and one acute angle. Notice that angle is 36 or less than 90. So these are all 4 new postulates that are shortcuts just for right triangles. Okay? Here comes a rule. The distance from a point to a line is the perpendicular segment that joins them. In fact, we talked about perpendicular segments at the end of last unit. Remember how we talked about from the vertex straight down is an altitude? And then from the other vertex straight down is an altitude. And from the final vertex straight down, oops, let's do that one better. But you get what I'm saying here. Obviously, my little sketch here isn't perfect, but we talked about the distance from a point to a line is that perpendicular. We talked about these altitudes last time. So that perpendicular segment is going to be discussed now. So what is the distance from C to line AB? Do you guys see it there in the picture? You got it. It's 4. That's this distance right here. And then finally, what is the distance from C to line AB? You got it. It's this distance right here of 1.5. Whenever we're talking about distance, and in this chapter on geometry, we are going to put U for units or just the word units, unless in the problem they told you it was inches or centimeters or specifically what the units are. Okay, let's fill in this little chart here. Perpendicular bisector theorem says that if a point lies on the perpendicular bisector of a segment, then it is equidistant from the endpoints of a segment. Because bisector means it's cutting that piece, that segment, into 2 equal parts. So what's the converse of that? If a point is equidistant from the endpoints, then we can use that to prove that it lies on the perpendicular bisector. And finally, if a point lies on the bisector of an angle, then it is equidistant from the 2 sides of the angle. And conversely, if a point is in the interior of an angle and equidistant from the 2 sides of the angle, then it lies on the bisector. So read those statements, pause the video here and read those statements to yourself a couple times. See if you understand how one statement's going forward and one statement reverses, and that's what the converse means, that it's proving the other thing backwards. Okay, what is the distance from C to B? And how do we get it? So take a quick peek from C to B. So notice that we've got equal side lengths here, and we've got this side length given up here. So what do you think the length of CB is? Are you noticing that this one is an isosceles? And that means that this right here would also be 21 units. Okay, now let's go talk about the angles. Same exact scenario here, where this time, if you know that this angle is 31, and you can see that these distances are the same, does that make sense that this guy right here is also going to be 31 degrees? There's our angle bisector. Okay, hopefully those made sense. Those made common sense to you guys. Now we're ready for some practice problems. Notice that they're expecting you to get this Pythagorean from the last section, and it's going to come into play again in this section when we're talking about the shortcuts for congruence for right triangles. So easy questions 1 through 4. Which triangle congruence is it? Do you see right here that we have leg and another leg? This is your LL theorem. Looking at the next one, do you see the hypotenuse and the leg? This is your HL theorem. Looking at the next one, do you see the hypotenuse and an angle? And a hypotenuse and an angle? This is your HA theorem. And finally, do you see the leg and the angle? And so this is your LA theorem. These theorems are all for congruence in right triangles only. Okay, they are not for similarity. They are not for congruence in regular triangles. They're for congruence in right triangles only. Okay, looking at 5, 6, and 7, just to give you an idea here. You see we're doing 5, 6, 7, 8, 9, and 10, and then we're done. So let's do these last 6 questions. Okay, so for this one, it says, what is the distance from point B to AC? And that was already given to us right there in the picture. Do you see it? It's 4.3 units of distance. Now for this next one, what's the distance from point B to AC? Notice that this one's not marked. So when we have a triangle side that's not marked, but we have right triangles, what can we use? We can use the Pythagorean. Now, which one do you want to do? Do you want to do 5 squared plus my missing side squared equals 9 squared? Or do you want to do 11.2 squared plus my missing side squared equals to this hypotenuse? Personally, I'm going to want to stick to the whole numbers because I don't want to work with decimals if I don't have to. So I'm going to write out my formula. Leg squared plus leg squared equals hypotenuse squared. And I'm going to get 5 squared plus my missing side B squared is equal to 9 squared, which is 25. And you need to subtract that 25 from both sides. 81 minus 25 gives us 56. And then we take the square root of both sides, and you're going to get that B is approximately 7.5 U for units. That is my missing side length that I had to be familiar with the Pythagorean in order to find it. What if you had called that side A and the 5 was your side B and you wrote A equals or is approximate? Totally fine if you called that A, totally fine if you called that X, as long as you label it in the picture and show what you're solving for. Okay, let's go try the last one. What is the distance from point Y? So I'm trying to find this missing side length. Again, I have 2 choices. I can do this triangle for Pythagorean, or I can do this one for Pythagorean. But since I don't want to deal with decimals, I'm going to go for this one with the whole numbers. So I'm going leg squared plus leg squared equals hypotenuse squared. And I've got 6 squared plus my unknown squared. You can call it X, you can call it B, you can call it A, whatever you want, is equal to the longest side squared. I get 36 plus B squared is equal to 100. We're subtracting the 36, which gives us 64. And when we square root both sides, the square root is 64. This one is a nice even 8 units. How'd you do? Are you feeling solid on your Pythagorean? Okay, finally, let's talk about these missing angles and such in these last ones. So notice if they ask for angle ABC, that's that big angle here. We know this little guy is equal to 15. So guess what? We know this little guy in here is also equal to 15. So what's ABC going to equal? Angle ABC is equal to 2 of angle ABV. And so angle ABC is equal to 2 of the 15 degrees, and therefore angle ABC is equal to 30 degrees. All right, looking at the next one, it says if XYZ measures 88 degrees, what's the measure of XYP? So we're looking at XYZ is 88 degrees. What's XYP? So this little guy right here. Okay. Well, if I know that angle XYP is going to be half of angle XYZ, right? Half of this big angle. Then I know it's going to be half of that 88 degrees that they told us in the problem. So my answer is just half of 88, which is 44. How'd you do? And last, we've got these little angles over here where if angle BAP is congruent, BAP is congruent to CAP, so we know that that's an angle bisector, then what is the length of AC? So they want this right here. And so remember that we've already got this 14 that's identified over here. So the work we would show is we would say that we can tell that AC is equal to AB, and that means that it's 14. And we're going to do a U for units because we don't know what the units are in that image. Okay, how'd you do? This is kind of like stuff you already know, but a little bit sort of new as well. So again, this is why I wanted to just summarize this and make the Apex quiz optional. How are you feeling on it? Are you going to go get some extra credit points right now and take the Apex quiz? Or are you going to stick to just the study guides?